you everyone for spending time and waiting for this presentation. And I will talking about our recent work about the physical-driven city scale simulation, but not only about earthquake, but also cover some of these the other disasters. So here is the outline of my presentation. So why we do the work, and we need a city information model to build up a database for this simulation. We need a physics-driven model for the earthquake simulation, and also for some other hazard like fire, wind, and the pandemic, and also to come to the conclusion. So first, come to our rehearsal background. So when we're talking about the city, actually that we are facing different kind of hazard. However, for most of the cities, some very severe earthquake hazards, it occurs. It don't frequently have this very severe hazard. So that we used to use some empirical model to predict based on the history to predict the future disaster. But in many cases, either we don't have sufficient data. For example, for some of the big cities in mainland China, we don't have very big earthquake for many years. And also because of some very quick development of the city, we don't have this data for these new cities. So that is our challenge we are facing, that we don't have sufficient historic data to predict the damage of disaster to the cities. So we think that we can turn back to these physics-driven models that, for example, when we're talking about earthquake, we can directly go to the nonlinear time history analysis, and we can use this dynamic simulation to predict the seismic damage, not only to single building, but to millions of buildings in a city area. And also we can do it for the fire or for the wind, that we can do the large area simulation for this disaster. So the advantage of this physics-driven model is that it is reliable, efficient, and adaptive to different situations. So I will talk about this later. Okay, so this is the first. Then secondly, we come to our database that come to the city information model. Actually, we are talking about the simulation for the regional scale simulation, but we have to confess that in most of cases, we don't have this possibility to build up a city model only for a single hazard. Well, actually, that we have a city with a different hazard, so that we need to have these models for different hazards. And also that we need to think about not only about the building level, we also think about the community level or the component level of data. So we to save all this data in that platform. So now we have a good solution that people call it a city information model. There's many different definitions for the city information model, but we can see that we can combine the GIS data and the building information model data to build up a city information model, so that we can use this building information model for some very special or very important buildings, and for this GIS data for some regional data, and we can manage all the data of the city on the same database. And this database can not only be used for the physics-driven simulation, but also can be used for different hazards, and also can be used for different scale. So detail of this work can be found on the paper on the bottom. For example, that we have, this is the Tsinghua University campus. So we can build the city information model of the entire area. We have all these buildings in the university, and some very important building, we can build a building information model for this detailed building. Then we set up a uniform data format, and then we can use this uniform data format, transform to different physics-based model, and we can predict the damage of different disasters to different scale of buildings. For example, that for the entire campus or for a very special building, based on our city information model, we can do the regional scale simulation for the earthquake disaster, for the fire disaster, for the wind, or for the pandemic. And also for the building scale, we can also do the similar work, but we can go more details to the earthquake, fire, wind, and pandemic. But the very important thing is that we combine all these simulations based on the single data platform. So we only to manage this data platform, and we can use this data platform to serve the disaster simulation for different disasters. Okay, then we can first come to our physics-driven regional earthquake simulation. And we have mentioned that our simulation can directly based on the structure dynamics, that we have the ground motion, we input to the structure models, we solve this structure dynamics equation, and we can know the city scale response of each building on the city scale. So the advantage of this method is that it strictly follows the fundamental structure dynamics. It can accurately represent the features of different buildings and different ground motions. And we have proposed these models for this for different buildings. For example, that for multi-story buildings, we can use the MDF shear model. Or for tall buildings, we can use this MDF flexure model. And also that we can, for some very special building, we can build these high fidelity models. And with this model, the advantage of this physics-based model is that we can directly compare the output of our simulation with some test data, or with some monitoring data, or with some really earthquake consequence. So that have the advantage is that it can very clearly show the accuracy of this proposed model. And furthermore, we can use the model to do the simulation. This is the one example. I think some of you have already seen it before, that this is our simulation for the Beijing CBD area. So we can input the simulated ground motion with 1679 Central Pinggu magnitude of 8 earthquake to the CBD area. We can clearly see the shaking of each building. For some very important building, we use the detailed models. For some conventional building, we use the MDF model. Then we can show the damage on different stories at different moments. So you very clearly see the consequence of the earthquake. And we need to mention that for most of these tall buildings, we don't have this empirical data for the seismic damage. So that is the advantage of this physics-driven model. And furthermore, we can give this simulation together with this UAV, the drone photos, so that we can use a photorealistic simulation model that we can show earthquake happens, the shaking of the model, and with very realistic result. And furthermore, I think that Dr. McClellan have mentioned that we can also use this model coupled with this underneath soil, so we can do the side-city interaction. That means that we have the ground motion into the buildings. This ground motion not only shaking the building, but also the reaction force of the building will come back to the soil. And we can see this contour show that the stress wave of the reaction force come off the building. So this will be significantly change the ground motion on the surface if you have a lot of density building on that surface. So this gives us a lot of opportunity to look at the some new phenomena of this seismic response on this density building area. The details of the work can be found in this paper. And this technology can be used both before earthquake and also after earthquake. For example, before earthquake, we can do the earthquake regional earthquake disaster simulation. Because we use the time history analysis, then we can know the EDP, that we can know the ground motion, the drift, the residential drift on each story. And with this EDP, we can combine with this performance group, and we can know that the resilience or the detailed consequence of earthquake, not on a single building, but on a regional scale. Here is one of our typical simulation. We simulate a magnitude of 8 earthquakes in entire Beijing area, and with more than 60,000 residential buildings. We not only simulate the seismic damage, but also we simulate the repair sequence of these buildings. Then here we show that the distribution of the workers after the earthquake. We can see that at the beginning of the earthquake, after the earthquake, most of the workers will be concentrated in the middle area of the Beijing city because we have the most important buildings to recover of the city function. But with time going on, that people are, the workers are moving to the suburban area because that we don't have sufficient workers to repair all these buildings at the same time. So that is will be very helpful for us to optimize the recovery procedure of the city after earthquake. And this technology, of course, can be successfully used in many cities in China. And also we can use this technology for the post-earthquake assessment. In old days, that we use the conventional method, we from the earthquake magnitude, we predict the density intensity and go to the fragility curve to predict the seismic loss. However, now we have a very densely recorded ground motion. We use this recorded ground motion together with the building inventory, and we do the nonlinear time history analysis. We can get a much better prediction of the seismic loss. So we developed a program called the Real-Time Earthquake Damage Assessment using city-scale time history analysis, called the REDAP, that we use the recorded ground motion inputted into the building inventory, and every time after earthquake, we can predict the seismic damage to the buildings. And you can see that the proportion of the damage to different buildings on different sites. And this technology has been used many times. Most of application is in China, and we have played a very critical role for the earthquake response in China. And two interesting examples is that after the magnitude of 7 Anchorage earthquake in 2018 and the magnitude of 7.1 earthquake in California in 2019, when we get ground motion, we can quickly predict the seismic damage to the buildings on that area. So the dark green means that no damage, the light green means slight damage, and yellow means the moderate damage. I think that this is the result we give to our friends in the United States in 1 hour after we get the ground motion. And I think this result is also very interesting. And in addition to the earthquake, we can also use this technology for some other disaster like fire, wind, and this COVID. For example, that in old days, we use the empirical model to simulate the fire, but they have many limitations. Then we can go to the physics-driven fire simulation. We can use the physics-driven thermal pump and radiation model to predict the spread of fire on a regional scale. And when we combine the building damage together with this fire spreading model, we can use this method to predict the fire following earthquake. Here is an example. We select a city in China. They have about more than 40,000 buildings. We inputted a design level based earthquake. So this is the city area. Here we show the seismic response of each building in this area. And after that, we knew the building damage. We can predict the ignition location. And with this building ignition location, we input the different weather condition because we based on the physics-driven model. So we can predict the fire spreading in the city area. And in addition to the fire spreading, we can also use this technology to predict to simulate the smoke or the fire scenario on the city scale. And we can compare this simulation with some actual fire falling earthquake case, and can see it's really very interesting. And we can also use it for the wind simulation that in all days, the empirical wind model have many limitations. We can combine this physics-driven large eddy simulation with the physics-driven time history analysis of building. So we use the computational fluid dynamics CFD simulation to know the wind on the buildings, and we use this time changing wind pressure on the buildings to do the time history analysis. Then we can know the shaking of the building and also the comfort assessment of the building and the potential level. So here is the typical case. We select the San Francisco tall building area. We build the CFD simulation model, and we also compare our CFD with some wind tunnel test, and they agree quite well. And then we can clearly show that how the wind goes through the tall buildings in the San Francisco downtown area. We can know the wind pressure on the building. It is quite different from our design case. And we also can know with this time varying wind pressure on the building, we can show the shaking of the building on this area. And with this shaking or the displacement of these buildings, we can further assess the occupancy comfort inside the building and also the potential wind comfort in the entire area. So this is the physics-based wind disaster simulation. We can go further to the pandemic case that in early last year, when the sudden breakout of this COVID in China, we are short of hospitals. So we need to complete some new hospitals in less than 10 days. So they give us a very limited time to do the exhaust air simulation. And we all know that the infection risk caused by the harmful air from the temporary hospital will be very important for the construction of the hospital. So we use our technology. We use our multi-level detailed city information model to build up these hospital models, and then we export this city information model to the CFD simulation. So with this technology, we can finish the CFD simulation for the hospital in less than 6 hours from building the model to the completed simulation. It's very efficient for the construction of this temporary hospital. And we also do some comparison to show that, of course, that the simulation accuracy and the simulation efficiency can satisfy the emergency demand. So here is the application example that in early beginning of the last year, during the breakout of the pandemic, we can finish the simulation or the analysis of a hospital in hours. So we can finish, for example, in January 28, we finish the first one, and the next day we finish another hospital in Beijing, and then another one in Wuhan, and another one in Beijing and Shenzhen. So we can reduce the exhaust harmful air risk to about 50% to 90%. So it will give a great help for the construction of these hospitals. And this is, I think, a very typical example to show the advantage of this technology, that this technology is very efficient, and because it is based on the physics-driven model, so it's very adaptive to different hazards. We have very little knowledge about this pandemic, the COVID, when it just come out. But with this technology, we can still use this our simulation method to help the construction, to help to control the infection of this virus for the construction of these hospitals. So finally, I come to my conclusions that we can use this physical-driven diagnostic simulation technology. We can use it, for example, for the entire San Francisco area. We do the nonlinear temperature analysis to know the shaking of each building. We can know the fire spreading in the city area, and we can know the wind or some other hazard. How do they go in through the cities, and how bring the damage to the buildings in the city? So this is the advantage of this technology. So that's all from my presentation. Thank you for your time. Thank you.